Okay, so the first thing I said that whenever we get these word problems that we pretty much have after this 12-week exam is to label what we know. So here's our DC source, 28. Here's a horsepower. So this I know is P out. Remember, because I said that when we're looking at a motor, we're going from electrical to mechanical. And I said that if you see horsepower, we know that that is the output power, because the mechanical will be in horsepower. We will not give the electrical power in horsepower. So there's P out, 96% efficiency, machine constant of kV. And this says assume frictionless. So that means that the power of the mechanical loss, right, is equal to 0. It would also say like rotational losses. So what we're being asked to find, we're asked to find Pn. We're asked to find the P of the electric losses, P electric losses. The supply current is I drawn at the motor at rated power in the torque delivered by a motor, right? So the torque developed or the torque delivered. So if I'm looking at my equation sheet, should not have done that. That's going to ruin my recording. Oh well. Okay, so here's the equation sheet. I can pull down right here to DC motors. And this is the stuff that I said you can deal in, right? Pn, kind of where just almost every problem can probably start with this formula on these DC motors, but we're just plugging in what we know and figuring out what we need to find. So we need to find the power in. We know the power out in horsepower, we'll convert it to watts. We know that the power of the mechanical loss is 0. We're gonna find this. And this was the one formula that isn't down inside of the box that we need, and that's the efficiency is equal to P out over P in. So right here, efficiency equals P out over P in. I can rearrange that to solve for P in, and that's going to be P out divided by the efficiency. And the P out is 1/4 of a horsepower times 746 watts per horsepower. And the efficiency is 0.96. And all that together, P in comes out to 194.27 watts. So now for the power of the electric loss, right, we said that the power gets split up into these 3 different parts, the electric loss plus the mechanical loss and the P out. Well, the P out was that 1/4 times 746. The P electric loss is going to be the difference, because this one we said was 0, right? The mechanical loss is 0. So this is simply P in minus P out, and that's 194.27 minus 186.5. So my P electric loss is equal to 7.771 watts. Now I need the supply current. P electric loss is equal to I. Actually, there's 2 ways you could do it. Nope, we can't use the P electric loss. Got to go back. So that could happen where you write down an equation, P electric loss, and then you realize you don't have an R. So it must not be that one. It must be this one. VDCIA, right? And so that's 194.27, it's supposed to be a 9, divided by 28 volts. And I comes out to 6.938 amps. The last one is the torque delivered, TD. We can grab that on the equation sheet. Right here in the middle, torque delivered, TD equals KVIA. TD equals KVIA. KV is 0.073, IA is 6.98. So the torque comes out to 0.506. So we could call it 506 millinewton meters. So it's a lot of terms, but if we just think of this idea from the equation sheet, that we have power coming in and power coming out, and there's losses along the way, and each part of those has formulas that we can grab, then that's my recommended way to solve it, is think about it as a power flow diagram with formulas for each of them. Like they have this right here, Pn equals VDCIA, and that helps, I guess, to have it right there in it. But if we just think of Pn is equal to these three parts, that's usually the best way to think about these motors. Something coming in, losses along the way, something coming out. Each part of those has a formula. In the middle, the power developed has formulas, the power out has a formula, the friction has a formula, the electric loss has a formula, the power in has a formula. But this right here is a pretty easy equation to think about the whole flow of it. All right, so there's number one.
Sure, so frictionless system always means that P mech loss is 0?
Yep.
Okay.
So now this is a linear motor. So once again, I said anytime that you see the word motor or linear motor, come straight over to your equation sheet. And the main thing that you need is inside this box. The only other one is the efficiency formula, if it's asked. Otherwise, everything that you need for motors is inside of here. Everything you need for linear motors is inside of here. So linear motors, I'll do the same thing. I'm going to label what I know. The B, I'm calling it B just because that's what it says on the formula sheet, but it's just the same DC source. It's steady state, so that means it got up to its full velocity. Right here is B. There is R. There is L already in meters, so we would want to make sure it's in meters if it was in another length unit. And what we're asked for is the steady state current. So that's I, and the steady state velocity, and on the formula sheet, that's U, when the motor is loaded to 100 newtons. And so we could say that's F load, right? But because it says the word steady state, that means it's also FD. Whenever it says steady state, F load equals FD. And you may have just gotten lucky and said FD was equal to 100 newtons, and you wouldn't have been wrong. That is what it is at steady state, and it's the only other place where a force is said. So if you just remember that force is in newtons, then you probably could get lucky with that one. So we're looking for the current. Where is current with what I have on the formula sheet? It's this first formula, the force developed equals ILB. So FD equals ILB. I'm solving for I. I is equal to 100 newtons divided by L, 0.91 meters. B is 0.8 Tesla, and I come out to 136.7 amps. Now I'm asked for velocity. Turns out the formula looks very similar. Right here, E induced equals UBL. Notice it's still the same BL. Now we're solving for U, but we don't know E induced yet. How can we get E induced? We can use this formula right here. We know V, we know I, we know R. We can solve for E induced. So to solve for the steady state velocity was 2 steps, but E induced equals V minus IR. And that's because of that tiny little series circuit. And this is just Kirchhoff's voltage law, that we get to steady state, we have the full E induced. It's as induced as it will be. It can't get any bigger. The V is 25 minus 136.7 times 0.025. That E induced comes out to 21.582. So then I can take my E induced formula is equal to UBL, rearrange it for U, 21.582 divided by 0.91 and 0.8, and my U comes out to 29.5 meters per second. There's number 2. Number 3 is a review of older topics. What we have is 16 alarm circuits wired in parallel. So there's 16 things in parallel. Here's a voltage source. The alarm currents are entirely identical. So that means all of their resistance is the same, and they each have 12. So to find total resistance, if I have 16 things in parallel, it's like 1 plus 12, 1 plus 12, right? All the way up to 16. Well, if I add 1/12 16 times, that's like saying 16 twelfths, right? I've added up 16 times to the -1. That's the same as reversing this, 12 sixteenths. And so it comes out to 3/4 of an ohm. Please don't give me 3/4 ohm. You would want to write, at least write 0.75. You could also write 750 milliohms. So now we have a voltage, total current draw. This is a DC, V equals IR. It says DC right here. V equals IR, we can rearrange for I, and we get 30 divided by 0.75, and that would give me 40 amps. Total power, there's multiple formulas for this. P equals VI is probably the fastest one just because we just saw both of them. 40 amps times 30, 40 amps for the current, 30 volts, and that comes out to 1200 watts. You could also write 1.2 kilowatts.